Hello. The topic that I'm going to cover today is alternating series test in chapter 9.5. The series of tests is different from the previous series test because in chapter 9.4, everything has to be positive value in order for the direct or limit comparison test to be applied. But in the alternating series test, the term has to be alternating between positive and negative value in order for the test to be applied. In addition, the previous test could determine either convergence or divergence, but the alternating series test can only show that the series converges. This is similar to how divergence tests can only prove the divergence when the term does not equal to 0. Compared to the series of tests we learned in previous sections, the alternating series test is far more quick and simple to apply. Let's take a look at the definition. The alternating series test is a series that infinity n equals to 1 a sub n such that the term a sub n alternate in sign for each consecutive value of n. You'll frequently see a factor of negative 1 over n in the terms when this occurs. This is also same as cosine and pi. So if you see the cosine and pi, you could apply as negative 1 over n. Let's now take a look at the theorem of alternating series test. Let a sub n be alternating in series. And in order for the a sub n to be applied as an alternating series test, there's two conditions to be satisfied. The first condition is that limit n goes infinity of absolute value of a sub n has to be equal to 0. If the limit does not equal to 0, then alternating series test won't apply, and it'll apply the divergence test to conclude the divergence. If the first condition is satisfied, then we can go ahead and check the second condition, which is that the absolute value of a sub n is eventually decreasing. Let's take a look at the example to see how this series can apply. As limits of n times to infinity, of the absolute value of negative 1 and plus 1 divided by n. Due to the absolute value, the negative 1 times negative 1 over n plus 1 will eliminate into limit n goes to infinity 1 over n. This is constant over infinity, therefore it's gonna equal to 0, and the first condition is satisfied. Then we can go ahead and jump into the second condition. For the second condition, we can refer to the hierarchy of growth. For the hierarchy of growth, there's no growth, which is constant. And then there's a logarithm of n, and the constant has to be greater than 1. Then there's a power function, n over c. This one is faster than logarithm, and the constant has to be greater than 0. Then there's a sub c over n, the exponential, and the constant has to be greater than 1. Then there's a factorial, and there's n over n. The logarithm is slowest growth, and the a sub n over n is the fastest growth. And it goes from slowest to fastest. So referring to the hierarchy of growth, the absolute value of -1 and +1 divided by n will lead to constant over increasing. So this series will eventually decreasing due to the constant over increasing. So the second condition also applies. Therefore, we can conclude that this series converges by the alternary series test. If you have seen the 1 over n, this is harmonic series. The harmonic series always diverges. But if you look at the -1 over n plus 1 divided by n, this is alternating harmonic series. This one is always converges. As similar to how the harmonic series doesn't have to reprove that the series diverges, alternating harmonic series can always converges, so it doesn't have to be reproved. Let's take a look at the second example. As limit n goes infinity over absolute value of -1 over n times 1 divided by 2n plus 1. This will lead to limit of n goes infinity n over 2n plus 1. Due to the absolute value, the -1 over n will eliminate into +1, and this will lead to the relational function of limit theorem, which has the same degree for the n divided by 2n. Therefore, we can conclude that it's gonna equal to 1 over 2, and this doesn't equal to 0. Let's recall to the chapter 9.1. It proved that the limit n approaches to infinity of the absolute value of the term is 0. If and only if limit n goes to infinity, a sub n without the absolute value is equal to 0. For this case, if and only if allows you to negate both true and false statement. Like how if P then Q statement can logically negate them, but if and only if can reverse the statement and negate the statement. Therefore, it can reverse to not equal to 0 on both statements. And the limit as n goes to infinity without the absolute value is also not equal to 0. Since the condition does not equal to 0, instead of alternating series test, we can apply the divergence test to conclude that the series diverges. So limit n goes to infinity, negative 1 over n times n divided by 2n plus 1 does not equal to 0. So we can conclude that this limit to n plus 1 diverges by the divergence test. Okay, from these two examples, we took a look at the both cases where the first example proved that the both conditions satisfies and the limit of the 0 converges by the alternating series test. And the second example show that the limit n goes to infinity of absolute value of negative 1 over n times n divided by 2n plus 1 is 1 over 2, which doesn't equal to 0. So the alternating series test doesn't apply, and the divergence test applied to conclude that the series diverges. Thank you everyone for listening.